Every time a map app routes you around a sudden traffic jam, or a social feed surfaces exactly what captures your interest, or your phone transcribes your voice in a crowded room, the algorithm asked to navigate across town will make wild, completely useless guesses. To improve, the algorithm needs a way to evaluate its own mistakes. It does this using a mathematical metric called a loss function, a single number that represents exactly how far off the algorithm's prediction is from the correct answer. The primary goal of the system is to drive that number down to zero. Driving that error down is incredibly difficult because these algorithms evaluate millions of simultaneous overlapping variables to make a single prediction. If you try to fix a high error rate by randomly tweaking millions of variables at the same time, the result is total system chaos. Adjusting one parameter might accidentally fix a mistake, but it will simultaneously break 10 others. You cannot guess your way to accuracy at this massive scale. Without a rigorous, systematic method to mathematically navigate millions of variables, machine learning collapses under its own complexity. The mathematical strategy used to solve this massive, tangled problem is extreme isolation. This 3D topographical surface plot represents a multivariable function, visualizing all the possible errors a model could make. To find the way down, engineers use a partial derivative. This calculation measures how the function changes when you adjust just one single variable, while strictly freezing every other variable in place. By slicing through the noise and looking at this isolated 2D curve, the algorithm can ask a simple binary question for a single data point. If I tweak this specific variable, does my error go up or does it go down? Once it knows the exact slope of that isolated line, the algorithm takes a tiny mathematical step down the curve, moving strictly in the direction that lowers the error. For the overall model to learn, this isolation process is repeated for every single variable it tracks, calculating millions of independent slopes. By freezing the surrounding variables, partial derivatives give computers a precise diagnostic tool to isolate cause and effect within a sea of chaotic data. Calculating millions of isolated slopes is only the first step. The algorithm still needs a way to combine all those individual adjustments into a unified direction for the entire system to move. This 2D contour map shows how all those partial derivatives come together to form the gradient vector. The gradient is a compilation of all those individual slopes, acting as a single arrow that points toward the steepest possible increase in the function. Since the objective is to minimize the loss function, the algorithm simply inverts the math. It calculates the gradient, turns exactly 180 degrees, and follows the negative gradient inward toward the absolute center, where the error is lowest. This iterative process is called gradient descent. The algorithm recalculates its position, finds the new steepest downward slope, and takes another step, continuing this cycle until it hits the absolute floor of the error landscape. In the real world, algorithms operate under hard constraints. They face finite processing power, strict time limits, or rigid logical rules. The math must find the lowest possible error without crossing those solid boundaries. The gradient vector acts as a mathematical compass, guaranteeing the most efficient path to accuracy while respecting the strict physical limitations of reality. Scaling this mathematical landscape up to modern neural networks requires optimizing across millions of distinct interconnected layers, far beyond a simple three-dimensional shape. In this network architecture, engineers use backpropagation to find errors. Applying the chain rule, the network traces an error signal backward from the final output, rippling leftward. It simultaneously calculates partial derivatives for every node, mathematically assigning blame to adjust weights accordingly. This massive simultaneous calculation happens continuously. It allows your navigation app to lock into a new route in milliseconds, or a search engine to parse your exact query instantaneously. If these systems lacked the mathematical capacity to evaluate their mistakes and adjust their internal variables, they could never adapt to new information. The software we rely on would remain rigid and highly error-prone. Partial derivatives prove their value millions of times a second. They are the exact steering mechanisms that transform raw, chaotic data into the intelligent tools driving modern life.